Okay, so let's recap. So yesterday, what we did was that we classified quaternions over the reals and the PI numbers. So these are called local fields in terms of how we write the classification in terms of Hilbert symbols. So the Hilbert symbol is just a pairing between the two arguments are in K cross, but in fact they were different by a square, then it's the same value. So the value is a function of K cross by the squares. And the way we define it is that the Hilbert symbol is 1 if the corresponding quaternion is isomorphic to the matrix. Or equivalently, this probably was how Hilbert symbol was originally defined, is that if you look at the quadratic equation x squared minus ay squared minus bz squared equals 0, this has a non-zero solution in K. The other case is when Hilbert symbol is -1, that's when the quaternion is not isomorphic to the matrix. This is equivalent to say that the quadratic form I said earlier has only 0 solution. And one of the part of the theorem we proved last time that is in the second case, these quaternions, they're not isomorphic to the matrix, but they're all isomorphic to each other. So over each local field, there is a unique quaternion which is not isomorphic to the matrix. It's also a division ring. So let's be more explicit. So we take, so last time we took a generator of this Z bar PZ cross. It's a single group order P minus 1. It's a generator. And the gamma to be the tension relative of this gamma bar. Then in the P odd case, the quotient of QB cross over the squares it's a very bad notation, right? The quotient is supposed to set, but whatever. You know what I mean. It's cosine represented given by 1 gamma P and P gamma. And part 1 of the theorem we said is that this Hilbert symbol is symmetric, and it's by multiplicative. I still feel like my linear is. More explicitly, if P is odd, we have this sort of 2 tables here. That's computed here, so that we can use it later. That's what the Hilbert symbol is. And there's a formula for this. A and B are sort of fill out the P part and graph the P part. And then the Hilbert symbol is given by this formula, where this UP and BP are Lagrange symbols. Okay, so today, once we're done with classifying quaternions over local fields, we're going to move on to quaternions over Q. I want to classify them up to isomorphism. So, a bit of notation. One of the things we try to kind of, we're going to use B, where this B is different from this B. We'll use a kind of a notion called a place B of Q. This is the standard notation. This place B of Q is either infinity, which corresponds to the Archimedean, the absolute, usual absolute value. This is something we call Archimedean line. Archimedean place. Because this is how, I guess, we learn it from elementary school. Everything like this, everything. This is usual rational. It's usual rational numbers, and with the usual absolute value that we've learned since like elementary school. Started out in Archimedean stuff. Or AP and prime. So we try to kind of the idea is that we equalize the importance of the Archimedean, the usual absolute value and the p-adic valuation or p-adic norm. So when we say a place, I could either mean infinity or p. So this is a non-Archimedean. Because Archimedes didn't know about p-adic numbers. I don't have to really use coefficient mark. And I can do, so over here, I have this notation of QP. Right, it's p-adic numbers. So over here, I'm going to write Q infinity. mean R, completion with respect to the usual absolute value. And if I have a quaternion D over Q, so I can get these two should go down here, but I don't have space. I can get I can tensor it up with Q infinity, or tensor it up with QB. So by tensor up, I mean that this is quaternion, and then it's a 4-dimensional algebra over Q. What I mean by tensor up is just basically replacing the coefficient. Instead of Q, I just use this real coefficient. Over here, I use p-adic coefficient. And all the roots are sort of the same. So this tensor is just mean that. So after a while, you will get used to it. So we do some notation. So we say D splits or unramified is unramified. At place B, if I tensor D with this QB, this is isomorphic to the matrix. Reinterpret what the classification, but in terms of the global object. That's right. In terms of a quaternion over rationals. Questions?
U work.
D?
U work, the opposite.
Is unramified? You want me to practice? That's spelling. Unramified. For example, if D equals QAB, then D splits at infinity if and only A or B is positive. Right? Because when A or B is positive, this is a matrix. And one more notation if you're probably going to see in the future if you do more math. It's called an indefinite case. In this case, we say B is indefinite. So when we say indefinite, I really mean that it's just about whether it splits or not at infinity. Okay. The opposite sort of the opposite location where this is D, we say D is ramified. Almost never people say not split. So I guess you could say non-split and people will probably understand. It's very strange sometimes. The notation is not symmetric. This is not actually. Remember that over a local field there are only two types, either matrix or not matrix, divisional. So the one is one case is called split is matrix, ramified is ramified is not. And corresponding to this indefinite, so ramified at infinity means definite. So the goal is to classify all the quaternions over Q. As it turns out that it's actually, the answer is very neat. If you start with a quaternion over Q, I can associate a set of places. I'm going to write sigma D. It consists of following sets, following places. It consists of, it's a subset of places of Q, namely a subset of prime numbers, including also possibly infinity, where this D is ramified. Namely, where the quaternion algebra is not isomorphic to the matrix. Or sometimes people write some sort of, you may probably also see something like gram D, because that's very ramified. No. Good enough here. There's a one-to-one correspondence. Between isomorphic classes of quaternions over Q. Basically, all the quaternions are to isomorphism. They are classified by this sigma D. We're just going to write down what the map is. So you start with a D, you send it to a set of ramifications that classifies all the quaternions over Q. More precisely, leave some space here. It's one word, like this. What you do is you start with a quaternion and send to a subset of places of Q. And somehow, first of all, the places where this quaternion is ramified is a finite set. It only ramified in finite places. So that's why, I guess, it's part of the reason why this is called ramified, but this is called unramified. Because ramified happens for finite times, and unramified happens for most of the times. So yeah. So it only ramified as finite many places, possibly infinity, or also possibly at some finite places, finite times. The next thing is striking thing is even cardinality. Somehow the deep part of the theory, my understanding. Let's just spell out what the theorem says. What the theorem says the following. So true, but I want to really explicitly write down what we really need to prove. So if D is a quaternion, has 3 parts. First, if D is a quaternion over Q, then first of all, the set of ramification is finite, and the cardinality is even. Note that we said this is a one-to-one correspondence. So that means that given any even subset of places of Q, even subset, sorry, sigma, then you can find the quaternion D such that sigma equals to sigma D. Right? By objection meaning that any finite subset you can always find a quaternion, which ramified set is that. And thirdly, and this map is sort of injective. That if D and D prime are quaternions over Q, and they're all isomorphic when you, so you want to show that the isomorphic classes of quaternions over here are completely classified by where it ramifies. What do you want to show? You want to show, okay, you have two quaternions if they have the same set of ramified places. What do you mean by they have the same set of ramified places? That means that the places where they're not isomorphic to the matrix are the same set of places. If you phrase it out the other way, is that they are local. When you tensor them with these local fields, they're the same. And then they're either both same as a matrix or both not the same as a matrix. Right. So you want to show that if the two quaternions are over here, they are sort of isomorphic when you tensor with all the local fields. Then they're isomorphic. So there are three parts. If you really kind of spell out what the theorem says. I'll say a little more. I will make a kind of a bigger remark on the theorem, and then we kind of go down proofs. Are there any questions about the theorem? Just classify all. Okay, remark. Well, the way we see this thing is that my understanding is that it's a typical example of the following way of understanding things is that we want to understand some sort of mathematical objects over the rational number, right? So often what we can do is that I can extend the scalar or the coefficients or whatever to these local fields. Oh, sorry. I should say collection of math objects over QB for each place. So over here I have some sort of a D, as I said. And over here I have dV for all V places, for all the places. And somehow, in general, if you want to study the math object over Q, it's often very, very complicated. Whereas understanding it over the local field, as we saw earlier, we have to, if you want to take show something in square. It's enough to show something in square in QP. In many cases, it's just enough to show it's a square modulo P, and then use Hansel lemma and just go all the way. So somehow often here, I can probably maybe reduced to questions about f of B, like corresponding like finite field. And I think finite field is considerably simpler than rationals. So that's general philosophy of attacking a general number theory question, that we first of all complete with respect to some prime number or the reals. We get some sort of so-called local object. So this is called global. This is global. And over here, everything's local. So local objects are usually considerably simpler. I guess that's general strategy in number theory. Step one is that if you want to understand the global object, you first understand it locally. That's step one. Step two is that you try to really understand this map. Like how much of the global information is captured by the local information. For example, whether this map is injective or not, which is true in my case. Like, not in that, like in the case of quaternions, the global one is uniquely determined by the local one. That's part 3 says. Also, you can ask, if you give local places, for each local place you gave some sort of data, do they come from a global data like that? And that's somehow part 1 and part 2 are addressing. Okay. So this is kind of global local sort of philosophy of mathematics. Of course, in terms of the entire mathematical industry or mathematical industry, there are many people that really just work with the local things. There are a lot of people who look at global relations, and I guess there are also people who just look at global things. You know, I think mathematics is kind of a big industry. Everyone is working on a specific part, and then you need to put everyone's effort together to prove a big theorem. That's how it works. So let me say maybe elaborate a bit more on the theorem here. So I have kind of a strengthened version, which maybe, depending on your taste, makes the same a little nicer in some way. Remark is that if your field is either Q or QP or R, possibly a global field, and given two quaternions, say P and D prime over K. Then you do the following crazy thing. You tensor these quaternions over K. So this guy's a 4-dimensional K vector space. The other one is also 4-dimensional. When you tensor together, you get 16-dimensional K algebra. As it turns out, this is at least for these three fields, it's always isomorphic to the matrix with coefficient in another quaternion algebra. Actually, for a unique, I should say. After isomorphism. So let's count dimension. This is 4 times 4 is 16. On this side, what does this mean? This means that, I don't know. That's what it is. You know, when you have matrix, you can do block matrices, multiplication. And each block, instead of putting a 2 by 2 block, I put in a quaternion there. You can still do matrix multiplication. So this is all together again. So each part is 4-dimensional. You have, what, 4 parts of 16-dimensional. So at least the matrix checks out. Okay. So now, what you just say on this set, all the quaternions over Q. There's a group structure. Then you just set D times D prime. It's a notation. This group structure, you define what is group structure. 2 elements, you're telling me what the product is. It's D double prime. Okay? And what is the inverse? Inverse is just itself. So it's actually a 2. It's a sort of 2 torsion. This is a very large set. It's an infinite set. And also, by this definition, you know that D tensor D prime is the same as D prime tensor D. So it's a Beating group. So this is going to be a Beating group. Maybe I should say a huge Beating group. Which is 2 torsion. Every element is killed by 2 because D times C is And you can really check that this works. It's going to take a while. Or actually, you can use a little bit of a theorem. Now let's do this again. What does the theorem say? So give it this name. Let me write it as Brouwer group. Okay. I'm doing the full notation. I put a 2. It's a very non-standard. Okay, go ahead.
What's the identity of this group?
The matrix. Sorry. Good question. I forgot to. See, my abstract doctor is very bad. I didn't even know. Because you see, if one of D is matrix, right? The matrix tensor with D prime. You just basically replace the Q of the matrix by that D prime. So get this two-vector matrix with values in that D prime. So identity times I of D prime equals D prime. And maybe I'll also say this one tells you that D tensor D. This means that D tensor D is 4x4 matrix with coefficient in Q. That's what it means. Because the tensor, you're going to get M2 of the identity element, which is the matrix. So you get 4x4 matrix. Right. So what am I? I said this set to be, I give it kind of a group structure. So let me write Brouwer group. But it's only kind of a part of the Brouwer group, actually. Two-quarter part of the Brouwer group. Okay. So what is the theorem? Says the following. The Brouwer group of Q. What you can do is that for each quaternion, you can get to the Brouwer group of the corresponding local field, which is tensor. Take the quaternion and extend scalar to the local field. And what does it say? It says that, well, for most of the places, you just get a matrix. Right. For most of the local places, if you start with the quaternion over Q, you extend scalar to that local field, you get the matrix algebra. So therefore, for most of the places, whatever you get here, take an element here, for most of the V, you will get the sort of the identity of corresponding group. So the image really lands in the direct sum of these local Brouwer groups. Each local Brouwer group is sort of the standard is just basically two things. There's this identity, which is a matrix. There's a non-matrix. I don't know what's it called. The other one. The other division element. So each one of these. So this is the isomorphic Z mod 2Z for each small piece here. And this is really a big group. Small. And now I can kind of rewrite. Yeah. Nicer way. Which is that Brouwer group of Q is isomorphic to, I don't know, it's a subset inside the direct sum of the Brouwer group of each local places, such that the sum of this is, zero. What the theorem says is that this quaternion is ramified an even number of places. So namely, it's sort of a 0 at almost all places, except that it's 1 at finite many, and even finite many, even places. And if you sum them up, that's 0 because we're modulo 2. But that theorem really says that the Brouwer group is isomorphic to exactly this huge group. And this thing you can think of as kind of just Z mod 2Z. So infinite copies. And this is sorry, this is going to be a product. Infinite direct sum of the F2 vector space, and you're taking kind of a hyper vector space of that, applying of that, and that's what it's a huge. But it still kind of have some sort of structure. Any questions about this? Yes.
Sorry, is the identity M4 or M2?
Identity is M2.
But then D tensor D is what?
Yeah, because M2 of M2 is M4.
Okay, you just wrote D tensor D is S number 2.
It is true. I mean, because it's almost like it's an M2 of M2. So by my definition,
Right, what goes inside?
yeah, it goes inside. Yes.
I think I have a similar question. Is M2Q a quaternion?
It is. By my, you can take, for example, AB to be 1. So, or any, as long as one of them is squared. Yes.
Why not the priority
Why is this? Because for each place there are only 2 quaternions after I remove them. The matrix and the non-matrix. Division. So there are 2. And okay, so the matrix is identity, the other one, the square is, because I said here, the square is 1, so the function. Other questions? I know this is, I just want to kind of show you a little. And in fact, maybe just a little bit. This is somehow a more general theory. Instead of working with quaternions, this thing kind of classifies also something called this thing. Classifies. I'll just give it a name. Look it up. Actually, I put it in the notes, but I won't be able. I won't have time to talk about it. So this classifies about central centrality. Quaternion algebra is one of the special cases of central central algebras. And for each local ones, you can sort of do the same thing. And you also kind of have a map like this, standard map. And you can describe the, and this map is also, again, sort of injective. And you can describe what the image looks like. And whatever we talked about in this lecture series about the quaternion algebras is sort of a 2-torsion version of this embedding. That's enough. I'll go back and talk about the theorems I wrote down. Back to kind of part 1.